A team consists of 2 driver operators, a coach, and a robot. The robot must be built from materials specified in the game manual and fit within an 18-inch sizing cube. After the match starts, the robot may expand. Each match is played with 4 randomly selected teams, 2 per alliance. Your alliance partner for one match may be your opponent in another. The game is played on a 12-foot square playing field with a foam tile floor and 1-foot-high walls. At opposite corners of the field are 2 corner vortices, red and blue. Between them is the center vortex, which can freely rotate. 4 beacons are mounted on top of the field walls. Below each beacon is a unique vision pattern for navigation. A white tape stripe leads up to each beacon. The field is divided by red and blue tape stripes. The Velocity Vortex game includes particles that are 3.75 inches in diameter. There are also 2 cap balls 21 inch in diameter. The cap balls are placed in the center vortex assembly. Teams place their robots on the field, touching the wall in front of their alliance stations. They may preload 1 or 2 particles, up to 3 per alliance. Before the match, field personnel randomize the 4 beacons. The match begins with a 30-second autonomous period. Robots can only operate by pre-programmed instructions. If a robot presses a beacon button matching its alliance color, the alliance is awarded 30 points. Also, an additional particle will be added to the field before the driver-controlled period begins. A cap ball in contact with the floor will earn an alliance 5 points. Each particle scored through the center vortex earns 15 points, and particles scored into corner vortices earn 5 points each. At the end of the autonomous period, if a robot is parked partially on the center vortex base or corner vortex ramp, that alliance is awarded 5 points each. If a robot can park fully on the center vortex base or corner vortex ramp, the alliance is awarded 10 points each. After the autonomous period ends, the field personnel introduce additional earned particles into the field. Then the 2-minute driver-controlled period begins. Now each particle scored through the center vortex earns 5 points. Particles scored into corner vortexes earned 1 point each. During the driver-controlled period, alliances may capture or recapture a beacon. Whichever color is lit up at the end of that match earns that alliance 10 points. The last 30 seconds of the driver-controlled period is the end game. During this time, robots may lift the cap balls to earn extra points. If your robot is holding a cap ball off the playing field floor at the end of the match, your alliance is awarded 10 points. But if your robot can lift it above the center vortex crossbar, your alliance earns 20 points. And if a center vortex is capped, that alliance gets 40 points. The game manual also lists various penalties to help ensure fair gameplay. For example, robots may not descore a capped ball. A robot may not extend above 29 inches before the end game. A robot may not damage the playing field. A robot may not pin another robot. This has been a brief summary of the Velocity Vortex game and does not include the latest updates. Please carefully read the game manual and the game forum for the complete rules. We want you to have fun and be competitive, but please remember, gracious professionalism, both on and off the playing field. Have fun and good luck this season. Go First Tech Challenge!
FTA's U.S. scorekeeper, are you ready? 3, 2, 1, go!
Hello, this is FTC Team 11355, Neal Team 6. We began in June of 2016 by building a Practice VEX robot that would autonomously navigate a maze without any user input. In doing this, we affirmed that our team's strength was in software and in sensors rather than hardware. When we first saw the game's kickoff in September, we set our design goals in order of priority. First, we would focus on the autonomous mode because that played to our team's strength in software. Second, we would focus on the ball cap lift mechanism. And third, the particle ball shooter. Our build process for the robot was first we would envision what we wanted to do next. Then we would CAD it, 3D print what was necessary, assemble, and test it. Whatever we learned from our testing, we would then envision what would fix it, CAD, print, assemble, and test it again and again and again until we got it right. When the team started, we had virtually no experience in hardware. We had to learn how to use machine tools and machine metal if needed. And on the software, we had to learn how to use Android Studio and work inside the Android environment, and then learn how to use the CAD tools effectively for the hardware side. Another part of what we had to learn how to do to build the robot was using the software Fusion 360, using that to 3D print parts, and then we had to learn how to machine metal bought from metal shops, and then combining that machine metal with 3D printed parts to build a functioning robot.
Hi,
I'm Neil Gallagher of the team Neal Team 6.
Hi, my name is Brandon Mail. I'm also on Neal Team 6.
My name is Joshua Fair, and I am as well part of Neal Team 6.
Shot and miss from the robot, Neal Team 6. Looking to trigger those beacons. Not quite able to connect. There they go. Nice and from that red team. Yay! 2 for 2. Will Alliance on the beacon presses. Will Alliance able to get one. Scurrying over to get partially on the platform.
We got both beacons.
Autonomously, picks up an object using a variety of sensors and brings it back to us. This image on the right here is our FTC robot we built for competition. I want to talk less about the robot itself though, but more about the sensors, specifically the 3D printing required to make them work. So here are some things we've 3D printed in the past. This model here is a shroud, or a bracket rather, for a sensor. You can hold 2 sensors on this bracket at different angles. This is another bracket, but for a VEX ultrasonic sensor. It's a different kind of sensor. And you see we have these holes here, with which we can fit a rod through. We can scan it on a servo motor, so we can put it at different angles. These 2 models here are shrouds for the sensors. The one on the left for the VEX sensor, and the one on the right for the sensor that we're currently using, which is the max body sensor. Now, the purpose of having a shroud on the sensor is to produce a more narrow beam pattern. We want a more narrow beam pattern so we can make our readings better, more accurate. And there's an inverse correlation between the diameter of the exit aperture of the sensor, which we can increase with the shroud, and the spread of the beam pattern. We'll get to more in a moment. First, here's the data sheet of our ultrasonic sensor for the VEX robot. It has a frequency of 40 kilohertz and a wavelength of 8.61 millimeters, a time period of 25 microseconds, and with a pulse duration of 250 microseconds. You're looking at about 10 cycles per pulse, and this is an image of what a sample pulse might look like. This is the data of the max body sensor. It has a frequency of 42 kilohertz now, but it has a 20 hertz reading rate, which was a limiting factor when we were programming with it. It has a variable pulse width and a beam spread determined by this equation here, where C is the speed of sound, not the speed of light. F is the frequency, which is 42 kilohertz. D is the aperture diameter, which is 16 millimeters in the sensor, but when we put on the shroud, it becomes 25.4. And theta over 2 is the half angle spread between minus 6 dB points. And what I mean by this is if you look at this diagram here, these would be the minus 6 dB points. And we want the half angle spread. So the half angle spread of this sensor would be about 30 degrees. Now here is a diagram depicting the beam spreads. Without the shroud, the beam spread is 30 degrees. When we put on the shroud, it becomes 19. These red lines are the new sensor we have here. This is a sensor that we bought rather recently. It's a more high-end sensor. It has an improved range resolution of 1 millimeter, which is going to give us more accurate readings. And it has a shroud built in, which gives us a beam spread of 11 degrees. Now, the surface roughness also affects the measurement. On a completely rough surface, the beams, you can see the reflected pulse is very clear. Now, if we extrude some shapes onto that surface, you can see it becomes less and less distinguished. And as we keep getting a rougher and rougher surface, the reflected pulse becomes less and less clear and defined until we get to a completely randomized surface, and you can hardly detect a reflected pulse at all. This is because when we send a pulse out to the surface, the pulse will scatter, which is why you can't see as clear of a reading. Now we have some other sensors on our robot. I wanted to skip the video to sort of save on time here, a little short on time. We have a gyro sensor on our robot, which we can use to detect its orientation on a field. We can use that in tandem with our motor encoders to determine its position in the field. We have an arm on our robot, which we can use to push buttons in certain places. And we do that. We use a color sensor on that arm, so we can extend the arm and detect a color on an object in order to make sure we're pressing the right button. We also have limit switches, which we use to detect pressure to make sure we're pressing the button with enough force. On the bottom of the robot, we have line trackers, which we use to detect white tape on the field, so we can align it to certain orientations, which will help us complete certain tasks. And that is the gist of my presentation. Does anyone have any questions?
Yeah. Let's get the question review all the way down. And take it away.
So I'm Neil Gallagher. This is my presentation on 3D printing in our makerspace. So this is the 3D printer we have. It's a WAN-powered duplicator i3. Costs about $400, so it's definitely on the cheaper end of 3D printers. I know the last presenter did in a MakerBot cost about $2,500, so quite a big price difference. This is sort of more of what our 3D printer looks like now. We have a plastic, just sort of a plastic bin from Walmart over top of it to sort of prevent drafts and whatnot getting into the 3D prints and prevent warping. So the two main types of 3D printing filament the two popular types are PLA and ABS. So PLA is a biodegradable plastic made from renewable raw materials such as corn starch, sugarcane. Aside from 3D printing, it's typically used for water bottles, plastic packaging material, plastic wrap, etc. It's considered to be more ecologically friendly than ABS. ABS is an oil-based plastic. It's a tough material that can be used to create robust plastic parts. Or robust plastic parts for everyday use. Has been traditionally used in electrical equipment, Lego bricks, things like that. Here's some different thermal properties of PLA and ABS. You see the melt volume index of PLA is slightly higher than ABS. Means you can maybe print a little bit of it, a little bit more of it in a given period of time. If the glass transition temperature at which heat kind of starts to affect the material, slumping temperature, which it starts to become malleable, melting temperature, it's the temperature at which it melts. And then you have the printing temperature, which is what you might set the 3D printer's nozzle to when you're printing with that material. So for PLA, a heat bed really isn't mandatory, as the temperature difference between the freshly printed material and the material that you've printed already is a little bit lower, so there's a less chance of warping. With ABS, it's basically a requirement, as the is the temperature difference between the freshly printed material and the material that you've printed previously would be much larger. So you have to have a heated bed, heated print surface to print on to sort of lower that difference and try to prevent warping. Overall, PLA is better suited for 3D printing beginners or for printing toys, as it's less susceptible to typical 3D printing problems such as warping. And printing ABS requires a bit more experimenting to find out the optimal setting between maybe your printing brand, your 3D printer, your filament brand, your 3D printer, etc. And here we have a little example of what a printed part warping looks like. You can see the bottom of it sort of curling upwards toward the part, so the flat bottom of it is perfectly flat. ABS is printed at a higher temperature than PLA, which greatly reduces the danger of clogging or jamming the nozzle. It requires less pressure feeding it into the nozzle. ABS tends to shrink with cooling, so the printer makes it warping and allows it to crack or split. To avoid that, use a heated bed. And like I said earlier, we have a plastic bin from Walmart over our printer. A lot of the more expensive printers already come with enclosures. This is sort of to prevent drafts from getting to the print and adversely affect it. Adhesion to the print bed is weaker than using PLA. This can result in a number of problems. And to solve a lot of these problems, what we did to solve it, what we might recommend, is using a slurry of ABS fragments dissolved in acetone. And what this does, when you brush that on the print bed, what this does is when you're printing, those first few layers, it's sort of, the ABS sort of melts together with the acetone slurry that you've brushed onto the bed, and that can greatly improve adhesion to the print bed. So what we're using for our 3D printer is in either of those two. It's polycarbonate. It's a high temperature material, has a good chemical resistance, it's really tough, good general heat physical properties, it's really heat resistant, it's great impact strength, has traditionally been used in making a bulletproof glass and compact discs, even though you couldn't print bulletproof glass. Here we have a picture of a polycarbonate part. Here you can see it's bolted to a metal bracket, sort of for a motor, and then pressure fit into some PVC pipe. To use polycarbonate, we had to make some changes to our printer. So the brand that we're using is Polymaker PC Max. The brand can change some things. Different manufacturing processes for filament can maybe change, has slightly different melting temperatures, etc. We have our bed temperature set to 200 degrees C. It's about the same as ABS. Your extruder temperature is set between 250 and 270 degrees C. This is a lot higher than the way how i3 was really ever meant to go. So that caused numerous problems. We have a glass plate on top of the stock sheet, and on top of that we have a build pack sheet. So we put the glass on top of the stock aluminum print bed because what was happening is the aluminum print bed was itself warping slightly. So we had a borosilicate glass piece that we put on top of that and just secured it with some binder clips. So that got rid of the bed warping problem. And on top of that we put a build pack sheet, as that's something that the Polymaker sort of recommends because polycarbonate might have an even harder time than ABS sticking to the print bed temperature, sticking to the print bed. And then we replaced the stock hot end on the Wanhao with an all metal hot end. So the stock hot end on it has, when you get it, it shoots with a plastic PTFE tube right in the middle of that nozzle. What happens when you're running your printer nozzle at 270 degrees Celsius, that little plastic tube runs a very good risk of melting and then just causing a bunch of problems. So we replace it with an all metal hot end, and that way we can more safely run the printer nozzle at much higher temperatures. Another problem running the printer to its absolute limits has caused is the power connector going from the power supply of the printer to its main board couldn't handle the current going through it and burned out. And see here's where the connector melted, and here's where it connected to the main board. Couldn't handle the current we were trying to force out of the power supply and gave out. Here's some 3D printed parts that we have that are in use. You can see here is a pulley mount. Here's some drawer slides for the robot. And so what this was meant to do is to securely pull pulleys and to lift sort of this ball in the competition. You can see them sort of in use. This is a picture of the competition. The reason that we needed to use polycarbonate, PLA or ABS, is we needed a material that could handle the force that we're putting on it. So together with everything, these maybe had to support a weight of 20 pounds with these drawer slides and everything and pulleys that had to secure in place. That's it. Any questions?
The maze via the shortest route. This presentation will focus more on the algorithm I wrote to find the shortest way out of the maze. So our solution for the maze tracking is we have 3 distance sensors on the robot, one facing forward, one looking to the right, and one looking to the left. For navigating to the object, we always follow the right wall. And then every decision that the robot makes is recorded into an array. Then once we get to the object, we put all of those decisions, the array, into the algorithm, and then that algorithm will then give us the fastest way out of the maze. Now, unfortunately, due to PC to Mac issues, I can't show the short video of the robot. So what does the robot actually record? Well, it records 4 different things while going through the maze. It records an L into the array when the robot turns to the left, as seen in this example here. It records an R when the robot turns right, as seen in these next 2 examples. It records an I, which stands for an ignore, which is when it sees a left turn, but then it continues straight because we're only following the right wall, as shown right here. Then the last thing it records is an S, and it records this when the robot moves forward a bit after a left turn. Now, this is really crucial to the algorithm because what this lets us do is distinguish between these 2 parts of the maze right here. An L followed by an S and an L means we enter in one way and then come out through a different path. Where if we have 2 L's, that just means we've essentially turned around. And so how does the algorithm work? Well, first I have this sample maze here. This S will be where the robot starts, and we'll say this blue star is the object. This red path here is the path that the robot will take getting to the object by following the right wall. And the green perpendicular lines are where it detects and ignore. And this up here is the decisions array that the robot would put out when going through this maze. And so how does the algorithm actually work? Well, it will manipulate that array until it can no longer make any more changes. So first, every double L is translated to a B, which stands for back. As I explained earlier, if we have 2 L's, we know we've essentially reversed. And then after that, it removes all the S's because this is all we needed the S's for, to distinguish that from whether we're just going up, turning left, going straight, and then going up again, or if we're reversing. So this is that same maze, and this is what the decisions array looks like after those 2 steps have been done. You see there's no more S's, and now there's some B's in there. So after that, sort of the main part of the algorithm is it goes through these 10 sort of equations, I guess, until it can no longer make them anymore. One of them is actually incorrect, but I'll get to that later. These 9 are the ones that are correct. And so for the first one here, LBR equals B. So we go left, we go back, and then we go right. Now they're kind of like functions where given one input, there's only one output. We know if in the array we have LBR, we know for certain it will look like this section of a maze, and so we can say that, okay, this is essentially a B, and we'll cut out that dead end there. And that's the same for all of these 9, where given this input, we know there's one output. And you'll see some E's in there, and that's because right here, if we have R, B, R, we set that to an E. And an E stands for we've traveled through there, but we're treating it as an ignore. So for the purposes of the program, E's and I's are essentially the same, but this helped me distinguish exactly what to do while coming up with this program. And so here we have the maze before in the decisions array, and now I'll go through the first iteration of the program. You'll see some of these dead ends like right here, they're gonna get cut off. First I'll just gray out everything that the robot doesn't see to make it easier to look at. And so now you'll see the dead ends be cut off a bit, and this is what it looks like after the first iteration of the algorithm. And down here, this is that situation kind of I explained earlier that doesn't technically work, but we're doing it for the purpose of this maze. And so it'll go through this over and over until it arrives at this. And once it gets here, it realizes it can't make any more changes to it, and so it says, okay, this is the fastest route from the start to the object. Well, we actually want to get out of the maze, so what we do to get from the object back to the start is we just flip the array, and then all the L's are changed to R's, and the R's are changed to L's, and that looks like this. This right here is the fastest way out of the maze from the object. And so going back to that situation earlier where I said it's not technically correct, that's right here, I-L-L-L-E-R. For that maze, we set it to a back. That's not actually correct. And that's because, as explained earlier, those simple ones, they're like a function. Given the input, we know what the output looks like. But for this, given the input I-L-L-L-E-R, there isn't one unique output. This loop here is I-L-L-L-E-R, but so is this section of a maze right here. That's not a loop. So we can't say for certain that this right here we can just cut off. And this is a problem with almost every loop. There's always multiple sections of a maze that will give us the same decisions array as a loop would. So how would we solve this? Well, we have to start introducing a new variable that we record, which would be the distance between our decisions here. So if we have the distances here, A, B, C, and D, if we see that A is equal to C and B is equal to D, then we know it is a loop and we can cut it off. For here, B is kind of equal to D, but A is not equal to C, so we know it's not a loop, and so we can't just cut this off and set it equal to a B. Now, how it will look like in the decisions array, well, if the loop starts with a right turn, the array will look like R, L, 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 I, and in between those characters, there's an indefinite amount of I's and E's depending on branching paths in the loop. It'll look the same with a left turn when it starts. But this actually doesn't cover every loop. There's still some, like, if we enter in the middle, what we'll have to do, we still only need to take the distances between our decisions, but we'll need to add certain distances and compare. See here, for this loop, we'll have to add distances A1 and A2 and compare that to C. And there's still more cases of loops that this won't actually solve. But what we can arrive at is a different solution where we can set up a coordinate system for our robot, and we know which direction it's facing and the distance between our decisions. So at every decision, we can give the robot a coordinate point for that decision. And then if we ever return to those coordinates, we know wherever we traveled is not needed and can be cut off. And that's the end of my presentation. Does anyone have any questions?